Good morning, everyone. This is Sangeeta, currently studying second semester of civil engineering in IIR College. So today I'm going to explain about self-inductance and mutual inductance. So self-inductance and mutual inductance are some fundamental electromagnetic phenomena which govern how circuits store energy, transfer power wirelessly, and shape signal behavior. So it explains from a tiny inductors in a smartphone to massive power transformers. So these magnetic principles power our modern world. So now we are going to learn more about self-inductance and mutual inductance and how they work. So the hidden force of a coil. So when current through a 10 millihenries inductor changes at 1 ampere per second, it generates 10 volts of back electromotive force, which is back EMF. So this invisible voltage opposes the change in current, acting like an electromagnetic brake. So the faster you try to change the current, the harder this magnetic brake pushes back. This property makes inductors essential for smoothing power supplies, filtering signals, and storing energy in switch mode power converters. So the hidden force of a coil is 10 millihards, which is a typical inductor value, and 10 volts, which is the back EMF generated, the back electromotive force, and 1 ampere per second. So what is self-inductance? The fundamental definition of self-inductance is that it is represented by L, and the self-inductance represents the proportionality between the magnetic flux linking a coil and the current that creates it. So the relationship is elegantly simple. So here, as mentioned, the formula L here N is the number of turns, and the pi is the magnetic flux through one turn, and I is the current. The unity is H, named after American physicist Joseph Henry. So a historical note is that Joseph Henry actually measured this effect in 1832, independently discovering electromagnetic induction before Michael Faraday, who published his famous law despite his priority. Faraday received credit because he published first and provided a more comprehensive theoretical framework. So this is the self-inductance, which is it basically represents the proportionality between the magnetic flux and linking between the magnetic flux, which is linking the coil, and the current that creates it. Okay, and coming to the solenoid formula, number of turns is represented by capital N. So square relationship amplifies inductance, and the cross section A, which means the area is nothing but the cross section. So the larger area captures more flux. And coming to length L, shorter coils have higher inductance. And the formula is L is equals to mu naught N square A by L. So for a long solenoid with air core, this formula relates physical dimensions to inductance. So the permeability of free space is mu naught. It is represented by mu naught, where the mu naught value is 4 pi into 10 power minus 7 H by M. So sets the fundamental scale. Solenoid example. Let us take an example by calculating L. L means length. So identifying parameters. Number of turns. N is equals to 100. Length is equals to 5 centimeters. And we've converted into meters, which is equals to 0.050 meters. And the cross-sectional area is A is equals to 0.30 centimeters square, which is equals to 3 into 10 to the power of minus 5 meters square. And now we are applying formula to that. And our formula for solenoid is L is equals to mu naught N square A by L. So here L is equals to 4 pi into 10 to the power of minus 7, which is a free space permeability value into N square. Here we have N number of turns is equals to 100. So we have substituted N square as 100 whole square into 3.0 into 10 to the power minus 5, which is A, which the cross-sectional area is 3.0 into 10 to the power of minus meter square. So we have substituted that. And we have small L, which is length. We substituted it 0.50 meters. And now we are calculating results. We have approximately 7.5 mu Henry. So this small inductance value 7.5 microhenries is typical for compact coils. The calculation shows how physical dimensions directly determine inductance. So more turns and larger area increase capital L, while longer coil decreases it. And energy stored in a self-inductor. So the energy formula. Inductors don't just oppose current changes. Inductors don't just oppose current changes, they store energy in their magnetic fields. The relationship is beautifully analogous to kinetic energy, which is U is equals to half Li square. So here U is in joules, which is energy, and L is in henries, which is inductance, and I is in amperes, which is current. So when we take a practical example, we are considering a 7.5 mu Henry solenoid, which is carrying 200 milliamperes of current, which is approximately 0.200 amperes of current, and the stored energy is, we're calculating U is equals to half Li square. So we have substituted half into L value as the solenoid value, which is 7.5 mu Henry. So we have substituted 7.5 into 10 to the power minus 6 into, we have to substitute I, which is current. So 0.200 amperes whole square, which is equals to 0.15 mu joules. So in real world context, while 0.15 microjoules seems tiny, it's sufficient to power a 5-volt LED for microseconds. So in switch mode power supplies, this energy storage and release happens thousands of times per second, efficiently converting voltages. So now, mutual inductance. What is mutual inductance? Our definition is that when current flows through one coil, it creates magnetic flux. If a second coil is nearby, some of that flux passes through it. So mutual inductance, capital M, quantifies this linkage. Okay, so the subscripts indicate flux from coil 1 through coil 2 or vice versa. And here's the form. And coming to key insight, which is symmetry. So remarkably, M12 is equals to M21, which is equals to N. The coupling is perfectly symmetric regardless of which coil drives the current. So this reciprocity principle is fundamental to transformer operation. And coming to the physical significance, M depends on geometry and relative positioning. So coils wound on the same core achieve high mutual inductance. Distant coils have minimal coupling, and this principle enables wireless power transfer and signal isolation. So basically, when current flows through one coil, it creates magnetic flux, as we know. So if a second coil is nearby, some of that flux passes through it, which is the mutual inductance. And two concentric solenoids and numeric walkthrough. Now we are considering nested solenoids sharing the same axis. So common transformer configuration. So let's work through a realistic calibration. Step 1 is the geometry setup. Let's take N1 is equals to the outer solenoid, which is having 1000 turns, and N2 is the inner solenoid, which is having 10 turns. And length is 0.5 meters, and area is 10 to the power of minus 3 meters square. And coming to mutual inductance, we have the formula M is equals to mu naught N1 into A by L. So I'm substituting the values here. 4 pi into 10 to the power of minus 7 is the free space permeability. We've substituted it, and N1 is the outer number of turns, so it's 1000, and N2 is the inner number of turns, which is 10. A cross-sectional area is 10 to the power of minus 3, which by length is 0.5. So when we substituted it, the value becomes M is equals to 25 mu Henry. And coming to the inductor voltage, it is if di1 by dt is equals to 2 into 10 to the power of minus 6 ampere per second, then E2 is equals to minus M into di1 by dt. So here E2 will be minus of 25 into 10 to the power of minus 6 into 2 into 10 to the power of 6, which we have minus 50 volts. So coming to the real world applications, this dramatic voltage transformation, which is a small current change producing 50 volts, power transformers, wireless chargers, and Tesla coil resonators. The minus sign indicates Lenz's law. The inductor voltage opposes the change that created it. Moving on. Coupling coefficient, which is K, measuring connection tightness. So definition and range. The coupling coefficient quantities how effectively two coils transfer magnetic flux. So K is equals to M by root over L1, L2. So this dimensionless ratio ranges from 0 to 1. So K is equals to 0, which is no coupling. Coils are magnetically isolated. So K is equals to 1, which is perfect coupling. All flux links both coils, and 0 less than K less than 1, which is partial coupling, typical for real systems. Okay. So power transformer example. A well-designed power transformer achieves K, which is approximately equals to 0.85, meaning over 85% of magnetic flux from the primary winding links the second. So this delivers greater than 80% of power efficiency. So poorly coupled coils, K less than 0.5, waste energy as strained magnetic fields. Okay, why it matters and what to do next. So energy storage, signal shaping, and power transfer. Coming to energy storage, inductors store magnetic energy, enabling power conversion, and switch mode supplies that power everything from phones to electric vehicles. And coming to signal shaping, self and mutual inductance filter frequencies, allowing engineers to design bandpass filters, radio tuners, and noise suppression circuits. And coming to power transfer, transformers are use mutual inductance to step voltages up or down efficiently, enabling long-distance power transformation and save household voltages. And mastering L and M lets you store energy, shape signal bandwidth, and build efficient power converters. So the core of modern electronics. So next steps are you have to apply these formulas for your next circuit design and then calculate inductance for your coil geometries, estimate mutual coupling between traces of your PCB and predict induced voltages from switching transits. So watch as hidden magnetic forces transform theory into tangible performance improvements. Thank you.